So in this video we're going to do some statistical plotting. So import numpy and matplotlib.pyplot in the usual way. Now we need some data, so we've got this extra file here. Let's just get this data here. Indent this nicely, so I'm going to take all these, and remember I can do a control and right square bracket to indent stuff as a group. Okay, so this is giving me some data. So what's this data? This is supposedly data about people's favorite colors. Okay, so we've got 7 different colors here. They've got names, and they've also got these hex codes, which is the usual sort of computer representation of colors. And then as the last entry here, we've got the number of people who've selected this as their favorite color. Now this data is a little bit dubious. There's going to be a separate exercise in a week or two, some kind of data processing exercise. You can see where the kind of main data set from which this stuff was extracted, and you can decide for yourself whether this is really a plausible representation of people's favorite colors. But for the time being, let's just suppose we believe it is. Okay, so we're going to need to reorganize this data a little bit. We need to, so here we've got a kind of 7 lists, each with 3 elements, but instead of that we need to get the codes as a kind of separate list. So let's just do this here. So codes is going to be so we can do this via list comprehension. We let x run through the entries in this data list, and then we take x0, which is the first entry. Right? So that's pulling out the just the first entries, and let's do the same with the other things. So the names, the color names is okay, so there's the counts, and then the names are like so. Okay, so so what are we going to do? Let's maybe make a pie chart. Okay, so maybe we'll go back to Google Gemini and say and ask for advice as to how we can make a pie chart. Okay, so here you've got values. That's going to correspond to our counts, and labels. That's going to correspond to our names. And then you see here it says plt.py, the values, label equal labels, etc. So there's a bunch of other stuff. So let's try that. plt.py. So, well, there's a couple of things wrong with this. Well, so firstly, it's given me this kind of a bunch of junk here that we don't really want to look at. We can just suppress that. That's kind of the output from this plt.py function. We don't really want to see that. We just want to see the picture. But if we put none there, then it'll kind of print the none instead of printing the output from plt.py, and printing a thing from none doesn't do anything. Okay. So that's given us a nice pie chart, but notice that the names are all wrong, right? I mean, this says dusk blue and it's green, right? So it's just chosen its own colors. So we actually want the colors to be equal to the things that we actually had. So let's maybe go back and see whether Google Bard told us anything about that. Okay, it doesn't really seem to be saying anything. So, all right, down here it's telling us. It says colors, customize slice colors using colors option. So, e.g., colors is some list of colors here. And here you see in this example, it's given colors as a list of these kind of hex codes, which is the sort of thing that we've already got. So, let's go back here and try that. And do notice actually we have to, as many things, we have to use the American spelling of the word colours here. Okay, so now this makes more sense. The green bit is green, the almost black bit is black, and so on. Okay, so there's our pie chart of apparently people's favourite colours. But maybe we'd prefer a bar chart instead. So that we could look it up with look it up in the documentation. Actually, yeah, maybe let's just have a quick go at that. So we got to find here, and this is so here's the full documentation for making bar charts. A bunch of examples down here. So we could read that, or we could just experiment, or try and ask Gemini instead. Yeah, so we'll get. Oh, yeah, so it's not called labels; it's called names. Let's. Okay, so there we go. So one problem is that this is all kind of overrunning itself. I mean, there's different ways we could try that. So let's maybe do. Okay, so we need to. I don't actually remember what's the. Let's try that. Okay, so that's the wrong thing. Okay, so so we can't remember the right syntax, so we go back to here and we say so it's plt.figure fig size equals. That's what we're supposed to do. So okay. So now we've made it wider. Still not wide enough to actually see all the labels. So we make it really wide, then we can see the labels. But then we don't. And we can make the colours right as well. Okay, so there's an example of a bar chart. Okay, one other thing let's do. We'll do a kind of histogram with frequencies. So let's generate some random head tosses. Okay, so. Actually, for a moment, let's not take the sum. Let's just do this thing here. So so I do heads. It's giving me a list of 10 random numbers in the range 0 and less than 2, so 0 or 1. So we've got 10 random zeros or ones. I could do so have the n equals 20. Now it's giving me 20. Okay, so that's like simulating a randomly tossing 10 coins. But let's take the sum of it instead. So now that's a kind of random simulation of the number of heads when tossing 20 coins. Okay, so let's kind of look at the statistics of this. Okay, so we're going to do let's actually make it a function. Okay, so we're going to have two numbers, n and m. So n is sort of the number of coins that we toss, but we're going to do that a large number of times. We're actually going to do 2 to the 15, which is around 30,000. We're going to do 30,000 trials of tossing 16 coins. Okay, so we're going to. So this is a list. We're going to do 30,000 trials of tossing 16 coins, and we're going to list the number of heads in each. And so now we're going to make a histogram. So we're going to use the function plt.hist for that. So for plt.hist, we've got the data x, which is the counts of these numbers of heads in each trial. And then we're going to split this. So the count, the heads, number of heads can be anywhere from 0 to n. So that's n plus 1 possibilities. So there's n plus 1 bins. The sort of assumption here is going to be that assumption built into the plt.hist function is sort of assuming that it's going to have continuous variables, not necessarily integers. And we need to sort of adapt to that. So we're going to sort of think of you have to supply the range. We're going to take the range from minus 0.5 up to n plus 0.5. So the first bin is minus a half to plus a half. The next one is a half to 1.5. The next one is 1.5 to 2.5, etc. In practice, we're always just going to end up in the middle of one of those bins, but it's convenient to arrange them so that so all the bins have the same size, all the width one sort of from half integer up to the next half integer, and then we're going to. So my notes, I have this density equals true thing. I can't quite remember why I put that in. Maybe we can just investigate in a minute to see what difference it makes if we take that out. So we're going to make this histogram. Okay, so let's do it. Okay, and it gives us a histogram like this. Okay, so it's interesting to sort of try and actually compare this with what the theoretical expectation. The theoretical expectation says that we should the number of things in each bin should be it should be sort of n in the ith bin. We should get n choose I times a half to the power n. So let's plot that. Okay, so we're going to okay, so we have to do. We're going to plot x value is going to be in the range from 0 to n, and then we're going to have our y values, and so we need the binomial coefficient. That's math.com for binomial coefficient n comma I. But you see, it's got a little twiddle here. So why is that? Because we haven't actually imported the math package yet, which we need to do in order to have access to the binomial coefficient. So we'll just do import math here, and now we should be okay. Math.com n choose I. All right, so now I remember why I have density equals true, right? So here what we've got is the the vertical scale is going from 0 up to 0.2. So what's going on there? I mean, the numbers, we should actually have rather large numbers. We did 30,000 trials, so they come in the middle. You should expect these numbers to go up to thousands or something. But because we put the density equals true business here, that's what it's function. That means it's just telling us the proportion of things in each bin. So we're saying that the middle bin has got about 0.2, 20% of the numbers. So X, which is the counts of these 30,000 trials in each trial. In particular, in total, so the count, the heads, 30% number of heads can be anywhere from 0 to n. So that's n plus 1. So about 600 trials giving us this middle thing here. So it's n plus 1 bit. So we're going to compare that against these things here. And here is going to be that n choose I assumption built into the plt.hist function is sort of assuming power n, which is that continuous. Actually, it's not probability of any integers. And we need to sort of adapt to that. So we're going to sort of think of let's make this be a different range. We're going to take a range from minus a. This is the curve that's kind of predicted by binomial distribution. Half to plus a half. The next one is you see that our counts to 1.5. The next one is 1.5 to 2.5. So that's another example. In practice, we're always just going to end up in the middle of one of those bits. But it's convenient to arrange them so that so all the bins are the same size. All the width one sort of from half integer up to the next half integer, and then we're going to. So my notes, I have this density equals true thing. I can't quite remember why I put that in. Maybe we can just investigate in a minute to see what difference it makes if we take that out. So we're going to make this histogram. Okay, so let's do it. Okay, and it gives us a histogram like this. Okay, so. It's interesting to sort of try and actually compare this with the sort of what the theoretical expectation. The theoretical expectation says that we should the number of things in each bin should be it should be sort of n in the ith bin. We should get n choose I times a half to the power n. So let's plot that. Okay, so we're going to okay, so we have to do we're going to plot x value is going to be in the range from 0 to n, and then we're going to have our y values, and so we need the binomial coefficient. That's math.com for binomial coefficient n comma I. But you see it's got a little twiddle here. So why is that? Because we haven't actually imported the math package yet, which we need to do in order to have access to the binomial coefficient. So we'll just do import math here, and now we should be okay. Math.com n choose I. All right, so now I remember why I have density equals true, right? So here what we've got is the vertical scale is going from 0 up to 0.2. So what's going on there? I mean, the numbers, we should actually have rather large numbers. We did 30,000 trials, so they come in the middle. You should expect these numbers to go up to thousands or something. But because we put the density equals true business here, that means it's just telling us the proportion of things in each bin. So we're saying that the middle bin has got about 0.2 or 20% of the numbers. So it was about 30,000 trials in particular in total. So 20% of that is going to be about 600 trials. So there's about 600 trials giving us this middle thing here. Okay, so and we're going to compare that against these things here. They n choose I times 2 to the half to the power n, which is that's going to be that's actually the probability of ending in there. And let's make this be in a different color. Okay, so there you go. This is the curve that's kind of predicted by the binomial distribution, and you see that our counts match up quite nicely with that. So that's another example of doing a kind of statistical plot using Matplotlib.